going fast, counting 1, 2, 3, and so on would eventually get us to the biggest finite numbers we've talked about so far. But there are two obvious problems with traveling down the number line in this leisurely way if our goal is to study and them numerical giants. First, counting up one at a time is incredibly slow. And second, the number should eventually reach after many times the present age of the universe, such as the googolplex, are so big that they can be written as full as decimal numeral. The advantage of realizing that it's possible, if only in principle, to get to colossal numbers simply by counting is that it reminds us that the only thing that different about such numbers is their size. They aren't different in data for smaller numbers like 3, 28, or 100 or 1016 any more than the distance across your hand is different in data from the distance to some far off galaxy. It's just a matter of scale. But as we've already discovered, the problem when dealing with seriously large numbers is devising ways to represent them that are compact, meaningful, and mathematically accurate. In the case of Graham's number, for instance, we know that it exists in some sense as long as a long string of digits, the last of which are it precisely defined is precisely defined as a and has a unique value, but there's no way actually to write it in full or in any other form such as an exponential using maths that were normally taught in school. That's why earlier in this book we started to bring in some new ideas such as the hyperoperator series so that we had more powerful tools to take us into big number territory. Now we're going to go further to the very limit of what's computable. To do this, we'll be hitching a ride on something called a fast-growing hierarchy. If we go back to the analogy with propulsion systems that can haul us across what vast distances at a blindingly high speeds, a fast-growing hierarchy is the equivalent of warp drive. Its mathematical technology hinges on three key concepts: functions, ordinals, and recursion. We've already come across each of these in various cases, but it will good, but it'll be good to recap to make sure we're starting on firm ground. A function in maths, remember, is just a relationship or a rule for turning inputs into outputs. So a function is like a mechanism that transforms one set of values into another set by always going through The same process. The process might be, for instance, add 3 to the input. We call the input x and the function fx, then fx equals x plus 3. We also have we can also have functions of functions. For instance, f(x) fits in fx as the input so that f(x) equals x plus 3 equals x plus 6. And if we can have functions of functions, then why not functions of functions of functions and so on, continuing with our sample and working right to left. Fx fits fx into fx to give x plus 6 plus 3 equals x plus 9. An ordinal, as we saw in the last chapter, describes a way of arranging a collection of numbers or other objects in a specific way so that there's a first, a second, a third, and so on. If the collection is finite, it can be put in order just by counting, by labeling its members with distinct natural numbers. But there are also infinitely large ordinals, the smallest of which is omega, The shortest ordering of a set that has aleph-null members in a fast-growing hierarchy. Ordinals are used to index the functions, which means that each function in the hierarchy is labeled with an ordinal.
Let's start nice and easy with a function that just adds ones, that just add, adds 1 to a number and call it f0. And if the number we want to apply the function is to if and so if the number we want to apply the function to is n, then f0 equals n plus 1. You may recognize this as the successor function we made earlier, a function that advances us down the number line, so to the next number. As you know, this isn't going to get us to really big numbers as time shown, but it's just counting up in the steps of 1. So let's move on to f1n. We've taken our first step, the fast-growing hierarchy, increasing the ordinal index, the subscript after the f, from 0 to 1. This new function fits the previous one into itself n times. In other words, where there are n ones, giving a total of 2n. Again, this isn't too impressive in terms how quickly it can get us into the land of the giant numbers, but it refers the process that ultimately gives a fast-growing hierarchy its immense power recursion. The next rung up the ladder, f2 fits f1n into itself n times, so we can write f2n with n with n2s. This is the same. This is the same as n times 2 to the n, which is an exponential function. Plugging in a value of say 100 for n, we get f2 100 equals 100 times 2 to 100 equals, or about 127 billion trillion. That's quite a jump. If n equals 100, we've gone from f0 100 equals 100 plus 1 equals 101 to f1 100 equals 100 plus 1 times 100 equals 200. So, to a number in the billion of trillion to a number in the billions of trillions, and that's just the start. The function f the function f3n involves a repetition of f2n and leads to a number slightly greater than 2 to the power of 2 to the 2 to the 2, where the power tau is n high. This brings us to the stage of 2 up arrows or tetration, the operation we came across earlier when making out a sort on Graham's number. If n equals 100, then f3n has already gone way past the capacity of the universe to contain it if we try to write out the result in full. Continuing in the same vein, f4n involves the 3 up arrows, f5n 4 up arrows, and so on. Each increase of the index ordinal by 1 having the effect of adding 1 more up arrow and boosting the number of up arrows to n minus 1. This certainly takes us into big number territory by everyday standards, but it amounts to nothing more than the hyperoperator series that we've already seen. Just adding 1 up arrows a time would never get us to Graham's number, let alone anything vastly bigger in a sensible amount of time. A new approach is needed. To reach truly colossal finite numbers, we need to transcend everything that's come before. We must enlist the help of numbers that are infinitely large. This is where a fast-growing hierarchy really comes into its art. when it taps the power of infinitely large ordinals to control how many times a function has to be performed. But before we can properly wrap our brains around this idea, we need to delve a bit more into the mathematics of transfinite or infinitely large numbers, in particular the maths of transfinite ordinals, the smallest. The smallest kind of infinity, as we saw in the last chapter, is aleph-null, the size of the set of all natural numbers, and the mathematics of it, we discovered, is both alien and counterintuitive. Add or take away an infinite number from aleph-null and the result is still aleph-null. For example, multiplication and division by finite numbers similarly has no effect. Aleph-null times a million is still aleph-null. You can even add aleph-null to itself and the result stubbornly remains aleph-null. Aleph-null is a transfinite cardinal. Cardinals measure how many members a set contains. If in the case of aleph-null, the set inclusion is that of natural numbers or 0, 1, 2, 3, although this has a fixed number of members, these members can be rearranged so that the set has different ordinalities or lengths. The shortest length of the set of natural numbers is the smallest transfinite ordinal, omega. The next shortest is omega plus 1, omega plus the next shortest is omega plus 1, then omega plus 2, then omega plus 3, and on and on. A key feature of all these different transfinite ordinals, which correspond to different ways of ordering the set of natural numbers, is that they are countable. This doesn't mean that you could actually count them all, but rather that there's a one-to-one correspondence between the ordinal and the natural numbers. Now, before we move on and see how all this applies to our fast-growing hierarchy, we need to know about a few other concepts to do with ordinal numbers. The first of these are the concept of successor ordinal and limit ordinal. A successor ordinal is exactly what its name suggests, as ordinal that immediately succeeds or comes after some other ordinal. The easy way, the easiest ways, the easiest way to think of this is that every successor ordinal is one greater than ordinal that precedes it. All natural numbers that are greater than 0 are successor ordinals. A limit ordinal is a non-zero limit of a sequence of ordinal, all of which are less than it, without itself being a successor. So, a free ordinal must be one of the following: 0, a successor ordinal, and a limit ordinal. You can reach a limit ordinal by adding 1, but or any other finite number to any ordinal than that is less than it. Following this definition, the smallest limit ordinal is omega. The next smallest ordinal after omega is omega plus 1, that is a successor ordinal. Infinitely many more successor ordinals follow until we reach the next limit ordinal, omega plus omega. This is a limit ordinal for the same reason that omega is, namely, it isn't the result of adding 1 or some other finite number or to any number that it exceeds in size. Corresponding to each limit ordinal is what's called a fundamental sequence, a sequence of ordinals that approach the limit ordinal but never reach it from below. In the case of omega, the fundamental sequence is just the sequence of natural number 1, 0, 2, 3. Any ordinal built using omega has a fundamental sequence based on it. So, for instance, the fundamental of the limit ordinal while omega squared has the fundamental sequence omega, omega 2, omega 3, and so on. In general, the last omega we can replace by its fundamental sequence, expanding multiplication and exponents as appropriate. So, for example, omega squared is rewritten as at last. We are ready to appreciate the true power of this fast-growing hierarchy by bringing transfinite ordinals into play. We'll see how the use of these ordinals to index the functions serves a springboard for reaching some of the largest computable finite numbers if we ever conceive. We started off with and so on, gradually working our way up to the uh, gradually working up our way up the hierarchy using natural numbers as indices. Now we're going to jump to f omega n, the function indexed by the smallest transfinite ordinal omega. But there's a problem we have to overcome in doing this. When we're figuring out the value of functions indexed by natural numbers, the first step was to reduce the index one by one and write down a recursive relation by sample. But we can use this approach when the index is omega, because omega is a limit ordinal and therefore isn't the successor of any ordinal. Instead, what we do is replace omega with nth number of its fundamental sequence, namely n itself, so we find that f omega n is just fn n. Now, to be clear, we are not saying that omega equals n, despite how it may appear. What we're doing is expressing f omega n in terms of finite ordinals smaller than omega, so that we can reduce the function to a form that's useful for these calculations. Perhaps you're thinking we may as well write fn n instead of f omega n and get the same result, but that would prevent the next crucial step, the step at which the full potential of our fast-growing hierarchy becomes apparent. As soon as we go from f omega n to f omega plus 1 n, something dramatic happens. Remember, when the ordinal indexes of the functions goes up by 1, this fits the previous function back into itself n times. If using a finite ordinal results in a fixed number of upper rows and using omega produces n minus 1 upper rows, then using omega plus 1 allows us to fit back into the number of upper rows n times, which amounts to a fantastic jump in the strength of the recursion. To understand this, think about a function f omega plus 1 2, which equals f omega 2, our recursion rule. Because we define f omega 2 to be the same as f2 2, we can rewrite f omega plus 1 2 as f omega f2 2, just replacing the innermost omega with 2. We can work out the value of the order of omega until we know what value the inner one will take. And it turns out f2 2 equals 8. So now we're left with f omega plus 1 2, which equals f omega 8. Finally, we can simply draw the most omega and get f 8, which is a number with the 7 upper. While this shows how f omega plus 1 can be used to feed back into the number of upper rows, it doesn't give a clear impression of the functions of some capability. This only becomes apparent as n gets larger and the corresponding number of feedback loops grows. Putting n equals 64 gives f omega plus 1 64, which approximately Graham's number. The next step, the fast-growing hierarchy f omega plus 2 n, burst into the totally new territory because it plugs all of the mathematical machinery used to reach the level of Graham's number back into itself. The result is a number we can write roughly as G with 64 levels of the G subscript. There is no hope of trying to grasp even vaguely what this meant, but it obviously represents a game-changing explosion in size. With each step up the hierarchy, there's a further extraordinarily steep rise in the number of recursive operations acting on what is already, from the previous step, a spectacularly large number. The countability infinite ordinals stretch away into the far distance, each successive one providing the basis for a recursive function utterly draws the power of the one before it. The omega alone from a sequence so long that it only ends when we reach omega raised to a power tower of omega omegas. This mighty ordinal, known as epsilon zero, is so fast that it can be described within our conventional system of arithmetic known as Peano arithmetic. With each step along with the eternal rod of omegas, the finite number can generate the recursion jumps by an amount that defies comprehension. But beyond the loftiest omegan power tower lie tier upon higher tier of yet greater infinite ordinals. First the epsilons, then the zetas, and on without end, as we saw in the last chapter in our exploration of infinity. This increasingly vast ordinals serve to define more and more powerful degrees on feedback. We finally reach a tremendously large ordinal known as gamma zero, or more magnificently the Pfefferman-Schmidt ordinal of the American philosopher and physician Solomon Pfefferman and the German mathematician Knuth, who first defined it. Although gamma zero is still countable, and there are countable ordinals beyond it, actual defining it requires of use the uncountable ordinals, ones that can be made for rearranging elements of aleph-null but instead require aleph-1 or more elements. This process is reminiscent of how the fast-growing hierarchy itself evolves. Just as we have to resort to using infinite ordinals in the fast-growing hierarchy to describe finite numbers, so we need to turn to uncountable ordinals to describe truly tremendous countable infinite ordinals. There aren't any adjective left to describe adequately the size of the infinite numbers to which the Pfefferman-Schmidt ordinal and order beyond it give rise by recursion. Nor does any mathematician have a brain big enough or clever enough to trustly grasp the immensity of the numbers the recursive techniques can spawn. Nevertheless, this number exists. They're thin in size and therefore lie on the familiar number line that we learn about as young children, and they could, in principle, be reached by counting up one by one from zero. In our case, to find the biggest number in the world, we've alternated between looking at the specific samples of large numbers and way of regenerating and defining them. Among the former, for instance, are the Gogol, the moser, and Graham's number. The latter include the hyperoperator sequence, Conway's chain arrows, and now this astonishingly powerful method of using a sequence of functions indexed by an endlessly increasing succession of transfinite ordinals. We've been talking about a fast-growing hierarchy rather than the fast-growing hierarchy for a good reason. There are different varieties. These varieties may differ both in the choice of initial function f0 and in the choice of fundamental sequences at the limit ordinals. The one thing that all fast-growing hierarchies have in common is that they are sequences of rapidly increasing functions indexed by ordinals. One of the first examples of the use of this concept was provided by G. H. Hardy in 1904. The Hardy hierarchy starts off in a very pedestrian way, and so on, following the same pattern for all infinite ordinals. Even when it gets to transmit indices, its base isn't exactly blistering. H omega n equals to n, H omega plus 1n equals to n plus 2, H omega plus 2n equals to n plus 2. Only by the time it reaches how it arrives at the level of tetration. But the Hardy hierarchy is historically important because it was the first time transient ordinals have been used to index a recursive function, and so is the ancestor of much more rapidly growing families of functions, such as the fast-growing hierarchy we described above. In fact, the two hierarchies are closely related. For any ordinal A, if A is the same as, so that, for instance, is comparable to Graham's number, the Hardy hierarchy eventually catches up with our fast-growing hierarchy, but not until its index reaches epsilon 0. Gogologists, whose pastime is the quest to define even larger numbers, fast-growing hierarchies because they're also used and were first developed more than a century ago in professional mathematics. Having been tried and tested in academia for many decades, they provide a solid foundation upon which enthusiasts can build more speculative ideas. In mainstream maths, fast-growing hierarchies are known, of course, to generate big numbers very quickly, but their main purpose is to serve as a benchmark for measuring the growth rate of other functions. Gogologists too use them in this way as a well established and respected tool for growing the string of different types of functions that also mushroom with incredible speed. Notable among these explosively growing rivals is something called the tree function. As the name suggests, a tree in mathematics can have the appearance of a tree that grows in the ground of a family tree with branches spreading out from a common trunk. Mathematical trees are a special variety of what in maths are known as graphs. Usually we think of graphs as being charts drawn on graph paper in which one value is plotted against another, but the types of graphs we're talking about in connection with trees are different. They are always representing data in which dots, called nodes, are connected by line segments called edges. If it's possible to start at the node, move to other nodes along edges, and then return to the starting node without repeating any edges or nodes, then the route taken is known as a cycle, or the graph is said to be cyclic. If it's possible to start at any node and travel to another node without repeating an edge or node along the way, then the route taken is called path, and the graph is said to be connected. A tree is defined as a graph that is connected but has no cycles, but both family trees and biological trees are also this kind of structure. If a unique number of colors is assigned to each node, then the tree is said to be leveled. Furthermore, if we assign one node to be the root, then we have a rooted tree. One useful property of rooted trees is that for any node, we can always trace back a path to the root. Some mathematical trees that have the same kind of branching structure as a real tree can be fitted inside others of the kind. They're said to be homeomorphically embeddable, which is a fancy way of saying They're similar in form or appearance, and one of them is like a smaller version of the other. Of course, mathematicians are a bit more precise about definition. They start with a larger tree and see how much of it can be pruned using a couple of different methods. First, if there's a knot except for the root knot that has that has just two edges, either leading into or away from it, that knot can be removed and the two edges join into one. Second, if two knots are joined by a single edge, the edge can be collapsed and the two knots compressed into one. The color of this new method is the color of whichever knot was originally closer to the root. If a smaller tree can be made by applying these two steps in any order to the larger tree, the smaller one is said to be homeomorphically embeddable in the larger. In 1980, in 1960, the American mathematician and statistician Joseph Kruskal proved an important theorem to do with this kind of tree. Suppose, suppose there's a sequence of them so that the first tree can only one node, the second up to two nodes, and the third up to the three, and so on, and that node tree is homeomorphically embeddable in any subsequent tree. What Kruskal found is that such a sequence always has to end at some point. The question is, how long can the sequence be? In response, American mathematician and logician Harvey Friedman listed in the Guinness Book of Records in 1967 as the world's youngest professor and assistant professor at Stanford aged just 18. They find a tree function, Tn. Friedman then investigated the output of the function for different values of n. The first tree consists of a single node of a certain color, which can be used again. If n equals 1, this is the only color and the sequence immediately stops, so that tree 1 equals 1 if n2 there's one more color. The second tree can contain up to two nodes, so it contains two nodes both of this color. The third tree also must contain only this color, but can only have one node, as otherwise the second tree would be homeomorphically embeddable in the third. Beyond that, normal trees are possible, so tree 2 equals 3. The big shock, as Friedman's one, comes when we reach tree 3. In a sudden explosion of complexity and proliferation, the number of nodes of a surpasses Graham's number and reaches the small ordinal, that extraordinary and small number we encountered in our travels among the various infinities in the fast-growing hierarchy. Among those two, 3 is definitely finite, as are all the numbers generated by the tree function for any specific n. Kruskal himself thought that any tree n will ultimately result in the tree that contains a previous tree, so that every tree n will output a finite result. Proving this for any particular tree, however, is neither easy nor quick. Friedman found a way to calculate how many symbols, so as plus or minus signs, exponents, or other mathematical symbols, it would take to prove that tree was finite. His answer 2 to up arouse 1000, or a power tower of 2 stacked 1000 high. The rate at which tree n grows is tremendous, bounded below by the fast-growing hierarchy of the smallest Veblen ordinal. Even the tree function, however, is totally outstripped in its growth rate by other functions that arise from graph theory. Friedman was defined tree. He has also devised what are known as the subcubic graphic (SCG) and the simple subcubic graph functions, like tree. This starts off modest enough, but then suddenly and sensationally inflated. For example, SSEG 0 equals 2, SSEG 1 equals 6. Then there's a rapid growth to SSCG 2, which approximately and ends with the digits. Thereafter, all contact with numbers from which there's any conventional form of notation is lost. The exact value of SSCG3 is unknown, but it's been found to be very much greater than 33, or 4 for that matter, 3333. Despite the fact that 3 SSCG are super fast growing functions, like them produce astonishingly large numbers very quickly, they are nevertheless computable. In other words, it's possible to write an infinite step-by-step list of instructions or algorithm to calculate the output for any given input. However, there are other functions that can be evaluated by a predetermined method, no matter what resources, such as time, memory, or proceeding speed, are available. They are said to be uncomputable, and among them are functions that eventually outpace and dominate every one of those we've looked at so far.